So welcome to Unit 5, Earth Resources, Real Life Applications. So we're basically at a point in the course now where you guys are all geologists. You know all the tools, you know how geology works, and basically now we're looking at how we could potentially make money in relation to geology and earth systems. And basically there's two categories. There's economic minerals, where you go out and you look for different mineral deposits. And in those mineral deposits, there are minerals that have market value that we value in society. And then the other option is petroleum, which is made up of natural gas and crude oil, which we also value and need in society. So really, economic minerals and petroleum are the two options to earth systems as careers, basically two big, massive categories. So I'll start it with petroleum. And petroleum is naturally occurring. It is a flammable liquid underneath the ground, and it consists of hydrocarbons. Now, in organic chemistry, hydrocarbons are just defined as compounds that involve both carbon and hydrogen atoms. So petroleum is just essentially a mixture of different kinds of hydrocarbons. Petroleum is like an umbrella word, so there's actually two types of petroleum. One is crude oil and one is natural gas. So it's not acceptable to use the word crude oil as a switch up for petroleum, because in doing so you could be omitting natural gas. So always kind of see it as natural gas and crude oil as the two options of petroleum. And anytime you use the word petroleum, it's very important that you specify which type. So crude oil is a mixture of hydrocarbons. It's a liquid underground, and when it comes out of the ground, it remains as a liquid. And that is the difference between crude oil and natural gas. Natural gas is also a mixture of hydrocarbons that could possibly be liquid underneath the ground, but once it comes out of the ground and hits atmospheric pressures and temperatures, it changes to a gas. So hydrocarbons are just chemical compounds that involve hydrogen and carbon. Some examples would be like methane, CH4, ethane, C2H6, propane, C3H8, and butane, C4H10, any of those. Octane, kerosene, jet fuel, any of those things would be basically seen as hydrocarbons. Now, a lot of the gases that I just defined for you, like if you had a reservoir that you struck, and you had propane and methane and ethane and butane and pentane all together in a reservoir, then we would say that you struck wet gases. The only time that dry gas is ever used is if only methane gas is struck. So if you asked a driller, what are you drilling into, and they said, we're drilling into a formation of dry gas, then they're expecting that when they actually do strike petroleum, it will only be methane, and as a result, they're able to use the description dry gas. So here's some hydrocarbons, what they look like in chemistry. So as you can see in the top left corner, we have C3 and H8, so that is a molecule of propane. We have C4 and H10 in the top right corner, so we have a molecule of butane from cigarette lighters. In the bottom right, we have CH4, so that is a molecule of methane. And yeah, so basically that's just what an hydrocarbon actually looks like. This is a fractional distillation chamber. I have a little bit of a problem with this particular description here. Okay, this should say petroleum for the very reason that I just explained a few seconds ago. So we're going to take the petroleum, we're going to put it into a furnace, we're going to heat it up to incredibly high temperatures. Okay, so heat is involved, and we're going to put it into this big thing here called a fractional distillation chamber, and basically the petroleum gets separated into different fractions based on boiling point. And so up here in the top, this would be your lowest boiling points, and down here in the bottom would be your highest boiling points. Just remember that lowest boiling points relate to fewest number of carbons, and highest boiling points relate to highest number of carbons. So these here would be more thinner types of petroleum, these here would be more thicker types of petroleum. So as you can see up here, methane, ethane, propane, and butane, they would all come under this category here because there's fewer than 5 carbons. So here you would have between 5 and 12 carbons, here between 12 and 16, here between 16 and 18, here 16 to 20. So as you go down, the carbons get higher, and that's the reason why the boiling point gets higher. So just keep that in mind. What you could get on a public exam is that you may have a fractional distillation chamber, but everything over here could be totally scratched out, and they could replace it with an A and a B and a C and a D, and they could say at which location, A, B, C, or D, would you get petroleum at the lowest temperatures. You'd pick A. At the highest temperature, so you would pick D. Fewest number of carbons, you would pick A. Highest number of carbons, you would pick D. And so that's basically how it works. It's kind of cool here. You can see where kerosene is, where jet fuel is, where the lubricating oils are, and that kind of thing. So that's how. In order to get petroleum, you need to have organic matter, and the organic matter that we are talking about here is not dinosaurs and whales and turtles and stuff like that. We're actually talking about microscopic organic matter, and so microscopic animals would be called zooplankton, and microscopic plants would be called phytoplankton. And so it's very important that you understand the type of organic matter that we're talking about. Here's just a picture of some zooplankton and phytoplankton as seen through a microscope, because otherwise, without a microscope, nobody would ever have seen zooplankton or phytoplankton before. Where do you get the most organic matter? Well, it's safe to say you would get the most organic matter close to the equator. If you think about like a tropical rainforest, is typically where the largest variety of biodiversity exists on our planet. So basically the factors that would determine that would be the amount of light. So naturally closest to the equator would give you the most light. Water depth, shallow of course, because we're going to need the sunlight to get through the water, so we can't have it too deep. Latitude would have to be low, closest to the equator for heat and light. Water temperature, warm is better than cool for having more life forms. Water turbidity is the cloudiness or the amount of dirt in the water, and we need a low water turbidity because we don't want our sunlight to bounce off particles of dirt in the water and bounce back. So we want clear water so the light can penetrate. And we also want an abundance of nutrients preferred by plants. We know that plants prefer phosphates and nitrates, so anywhere you get a lot of those nutrients, you're going to get a lot of plants. So basically that summarizes where we get the most organic matter on our planet. Then we're going to need to preserve that, and basically we're going to need an environment where we have anaerobic conditions, a low oxygen environment, so a swamp or a lagoon. In the event that you don't have a swamp or a lagoon, what can you do to ensure that we have no decomposition of organic matter? Well, we're going to have rapid burial of the organic matter by fine-grained sediment, mostly mud or silt. And that got to happen rapidly because we can't have oxygen, because if we do, we'll have bacteria and also have decomposition. So here's a picture of a swampy type environment. The formation of petroleum is certainly linked to the system. So in Unit 1 we talked about the system, and Earth is a system that's made up of 4 parts, and the 4 parts are gorillas always have bananas, and that's the order in which the 4 spheres occurred. So we have a geosphere and an atmosphere and an hydrosphere and a biosphere. All that we want you to do here is to consider the formation of petroleum and how that relates to each of the 4 different parts. So naturally petroleum is found in the ground. Petroleum, if you think about natural gas comes from plants, microscopic plants, and plants do photosynthesis, which requires them to take carbon dioxide out of the atmosphere and sunlight out of the atmosphere. Those same plants and even zooplankton for crude oil need water in order to live. And naturally, petroleum comes from living things, which is the biosphere. So that's just me giving you a couple of examples to prove how the geosphere, atmosphere, hydrosphere, and biosphere is related to the formation of petroleum. Once you have your organic matter, that organic matter got to get buried rapidly by fine-grained sediment. Now, the minute that happens, we have a material called kerogen. So kerogen is just basically a mixture of the organic matter with the sediment. And that kerogen is going to undergo maturity. And we call that evolution or maturity, whatever you want to call it. And typically that takes place as you have more burial, more heat, and more pressure. And the evolution takes place in 3 different stages, and I always try to remember them as don't call me, and don't stands for diagenesis, call stands for catagenesis, and me stands for metagenesis. So they are the 3 stages that the kerogen must go through as it starts to get buried. Now, diagenesis, typically the burial is fairly shallow. Temperature and pressure is just slightly above normal. There's even a little tiny bit of decay of the organic matter, but not much. Now, gas is released at this stage, but there is no oil, so the kerogen may mature enough that methane, carbon dioxide, and water vapor could potentially get released. As burial gets deeper and deeper and deeper, and you get more temperature and more pressure, then the organic matter matures more and more and more. And basically the maturity is to a point that we actually get first oil and second gas release. So this is the sweet spot. So if we could have our way, all organic matter that gets buried rapidly by fine-grained sediment or deposit in a swamp, we would like for it to get to catagenesis. That is your oil window. If you get to metagenesis, then essentially it's gone too far. Now, meta makes you think of metamorphism. The kerogen has not matured to a metamorphic environment in this case. However, the temperature and the pressure is really close to metamorphism, okay? At this point, the only hydrocarbon that actually gets released is methane. So that's all you get is just pure methane. And so, unless you're looking for a reason to have methane, and there's not a lot of people that just use methane, so I kind of like to think of metagenesis as gone too far. You're gone past the oil window, and you only have one gas, dry gas, that you really don't want. Now we're at a point that we have our organic matter. The organic matter has went through maturity, hopefully got to call, which is catagenesis, so you have some oil and you have some gas. Then what got to happen is that it has to go into a trap. Just think about the word trap. That petroleum got to be trapped so that you can drill it, and all of it be in one location together so you can drill it and produce it out of the ground. Now that brings in 3 other categories of rocks. It brings in a source rock, a reservoir rock, and a cap rock. The source rock, that is the rock where the organic matter got buried. So the organic matter got buried rapidly by fine-grained sediment, and then that sediment got slightly lithified, which means turned to rock, and it went through don't call me. The rocks that typically apply here would be shale and limestone. They're the 2 rocks to watch for that would apply to that. The petroleum is going to leave that source rock and it's going to go out into the sponge. And I always like to say sponge because everybody can picture a sponge. A sponge got holes in it, which we call porosity. And those holes are connected, which we call permeability. So a reservoir has the ability to store petroleum and for petroleum to move through it. Now, rocks that we will do that will act as a really good sponge would be conglomerate, which we've done in this course, sandstone, which we've done in this course, limestone, which we've done in this course, and there's another one that's very similar to limestone called dolomite. So they are the 4 options for reservoir rock. Then once it gets trapped in the reservoir, it needs to get capped off so it doesn't escape. And so naturally a cap rock has to be very, very impermeable so nothing can get through it, and the only rock that we've done that applies to is shale. So here is a picture of shale down here on the bottom left and a picture of compact limestone on the bottom right. They're the 2 examples of source rocks. That's where the kerogen basically gets matured and undergoes don't call me, and it's also where the organic matter exists. The reservoir rock is noted by high porosity and high permeability, hence the reason why I referred to it as a sponge. The petroleum comes out of the source rock and goes into this reservoir rock and hopefully gets trapped and remains in the reservoir. So porosity, we said, is all about the space inside the sponge or inside the rock. The more porosity, the better. Okay, the more petroleum it can move. Store, I should say. Typically, the bigger the porosity, the more rounded the particles, the more sorted the particles. Typically, what that means is you're going to get more porosity and a higher likelihood that those pore spaces will actually be connected, and that takes into account the word permeability. Remember that permeability is all about the rate of flow through a rock. So in this particular picture, we have a picture of conglomerate and we have a picture of sandstone, both that can actually act as sponges. So in these 2 rocks, there are open spaces and connected spaces that can store and allow flow of petroleum. The cap rock got to be an impermeable rock so that it traps the petroleum in so it cannot get out. And a really good example of a cap rock is shale.